That's right. We're here. We're back. And it's the last live stream of the year. Last live stream of 2023. And we're talking about some really cool stuff today. So, welcome to the stream. If you were watching this live, thank you for joining live and coming on and type in chat where you're from and where you've been, what you're doing for the new year, all of that. We are going to talk about some cool stuff today. If you're catching this on demand, you don't get the opportunity to communicate back and forth. You don't get to be in chat, but you do have chapters. And so as we're going to be talking about today, we're talking about some memory topics. And it sounds kind of boring, but yeah, it's one of the most important things that you can really understand. So if you are joining us for the first time live, like I said, drop in chat what you got going on and just say hey. And yeah, if you are joining on demand and you are not subscribed, consider subscribing. Either way, if this is helpful, hit that like button and get it out there. The channel's been growing great, and you are the reason why. You are the reason why we are growing, and you're the reason why we're here. I mean, I guess people that know me know that I probably like to hear myself talk too much, but that's not why I want to be here. I want to help you guys. I want to be able to get out there, get all this information out there so that it can help you out in your journey. Today, we're talking about DataBlocks, data types, arrays, and then we will actually get into the most difficult, the most mind-bending and mind-breaking and possibly program-breaking topic: indirect addressing and pointers. And so, yeah, glad you're here and glad you're on the stream. And we're going to get started off a little bit today talking about the basics of TIA Portal. And really, that's one thing I should say, and is that this isn't just for TIA Portal. I'll be working in TIA Portal, but everything, to turn that down on your end, seems loud in my ears, but it doesn't look like it's too loud, the music that is. But I will be working in TIA Portal today. We'll be working with a little bit of a couple of different things. We're going to talk about DataBlocks at first, DBs. So if you are new to Siemens and you are new to programming in either a 1500, 1200, or if you're programming in a 300 or 400, because there's still millions of those processors out there, all of what we talk about today will be applicable. So yeah, what we're doing today is improving our lives, improving our programming, and taking you to the next level. That's why I've kind of took my style to the next level. We're ushering in 2024 with a new style. So what we got going on today, the first thing we're going to talk about is DataBlocks. So I'm going to bring up a DataBlock that I have written. If I get over here on, nope, I want to be on that side so I can look up. So we're going to be talking about DataBlocks starting off, and I'm going to turn, so what I have here is a DataBlock, and if you're not familiar with what a DataBlock is, it is an organizational block, or I shouldn't say organizational block, because there are organizational blocks. You have OBs, FBs, FCs, and DBs. So when you're working with Siemens programming, those are the things that when you go and say program blocks, add new block, it brings up OBs, FBs, FCs, DBs. And so a global data block is just an allocation of memory. So we can just create this data block called my DB. And global means that it can be accessed by basically anything at any time. So any function call, function block that you write can access a global DB. You can pass a global DB around, and what we will talk about later is you can point to a global DB with a pointer in pretty much every circumstance. So let's just create this automatic. One thing about a DB is it has a DB number, and these aren't too important. You just don't want to have too many of the obviously you can't have too many of the same type. So the DB number is actually kind of the actual memory location. The name is just symbolic. And so if you have a couple of things that are named differently but have the same DB number, then it's the same place. So I don't know how you would get into a situation like that, but just remember the important thing is the numbers, not the name, because ultimately Siemens processors are not symbolic. So in TIA Portal, if you don't know what that means, in TIA Portal, you have a lot of tags, and the difference between a symbolic or direct addressing and a symbolic addressing is in Allen Bradley, when you make a tag on the back side, there are ways that you could go through and specify the actual memory locations, but in general, a tag is a name, and it represents some data, and you personally as the programmer don't have to keep up with where those are. And in Siemens, for the most part, you don't either. And in the previous version, the SIMATIC Manager, so for the 300s and 400s, you had to keep up with it a little bit more than you do in Portal. In Portal, you can do tags, you can do symbolic addressing, you can do all of the things that you might be used to if you're coming from Allen Bradley, but you ultimately are directly tied to a memory location, and that's going to come up later on when we're talking about Portal. But the reason why you want to use DataBlocks is because it organizes your data. And I want to show you something. I'll just pull up the main program suite here, and I have this little that's not your Discord, that's my Discord. I have this little block here that I've written, FB1, and we'll be talking about that and using that a little bit more here in a second. But what I want to point out is I've made a little tag here, and I can go through and make logic and just type in symbolically my tag, and it says, hey, that doesn't exist. And then I can just go define tag and say local temporary or global memory, and then put it in the tag table, and it makes me a tag for that bit, and it makes it there. Well, I haven't programmed much in Allen Bradley, but from what I've seen, and most of the people that I've watched program Allen Bradley, they're used to doing this. And so you come in and say, hey, I need a tag. Here's your tag. There you go. It's set up, puts into a tag table, good to go. Well, what happens though is these are all in M memory, which there's inherently nothing wrong with using M memory. And you'll hear me joke around about using M memory, and that's how everybody knows that you're not a Siemens, originally a Siemens programmer. And here's why: because ultimately if you're automating a system, you're wanting to reduce the amount of work that you are doing. You want to make your life easier on something. And while doing it this way and putting things in memory is easy up front, you can't go through and easily modify this program. And I'm gonna have to mute that because I'm getting distracted. Mute tab. So you can't easily modify this program and reuse this code. So basically, you're always going to be having to go in, and if you make a new machine, if you make a new project, you're never going to be able to reuse this work. You're going to have to modify that over and over and over again, which you might be sitting back and thinking, well, like, duh, like everything's well, that's where you're going to take on to the next level. That's where you're going to improve in your life. That's where you're going to become kind of this guru of programming, is once you realize that, hey, I don't have to rewrite everything every time. So one thing that you can do to make your life easier is by using DataBlocks. Instead of just using tags in memory, put everything into a data block. And if you want my tag like this, and you want that Boolean, put it into here. And instead of referencing over here, to my DB dot my tag, and there you go. That functionally works the same. And the reason why you would want to do this is because you can take this DB, my DB, and copy and paste it. So you can drag this into another project. You can take that DB, that designation, and you can take that memory and put it over there. And you might be sitting here saying, well, Jason, you could copy a tag table too. Yeah, you can. But what happens if that memory location has already been used on the processor? So that in memory that your tag table is tied to, what happens if you've already used that in memory? Well, you're going to have to go through and manually change all of those things. If you catch it, you might not even realize that you've double named it. And now you have two tags. Remember, we talked about this situation earlier. You have two symbols, you have two tag names that are pointing to the same memory location. And so you now have this kind of race condition to where you are, you're trying to figure out which one has control, which one's actually taking care of it. So, because if you import a data block, you get to pick the DB number. And while inside the data block, it's in the same location, you have changed the DB number. And so now it's DB10, whereas on your original system, it might be like this one, DB4. And so that tag symbolically is still the same thing. It's still my DB.myTag, but down on the core level, it is, it's actually DB10.dbx whatever, dbx0 or 0.0 in this case. And that goes to the next thing. So there's a couple of different ways in TIA Portal. If you are used to using step 7, so the SIMATIC Manager, and you're used to programming on 300s and 400s, you are used to seeing what I just said. So in this case, if you are fairly familiar with Siemens, especially in SIMATIC Manager, you might be like, hey, this is totally symbolic. This is hidden. It's not saying that my DB, like I don't see DB4 DBX 0.0 like you would be used to. And here's why. Because when I created this by default, TIA Portal creates the data block in what's called optimized block access. And it makes it to where all of that, the DB numbers and DBX 0.0, DBD, all the stuff that you're used to if you're used to step 7 like SIMATIC Manager, that's all hidden because it's all really more symbolic. Now, Problem is, there's a lot of stuff that you can't do with optimized block access on. So what I'm going to do is show you how to turn off optimized block access. So you go through and you right click MyDB, go down to properties, and you have to be offline to do this. And it's just a check block that says optimize block access. So take that off. And it says the retain settings, blah, 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 all of this stuff. You have to recompile the program, say, okay. And now you go in, say this, and we're going to recompile. And guess what, my friends? There we go. You have what you're used to in step 7, version 5.5. So there's your DB4 DBX 0.0 that you might be used to. So if you're looking for that and you need to use it, turn off optimized block access. Now, that's really the basics of DataBlocks. And we can go in here, and DataBlocks can house really anything. So we can have my int, and we can have integers. We can do my real. Real. We can have reals. And so forth and so on. So one thing that you'll see a lot that I use on here is what's called PLC Datatypes, but you might be used to them being called UDTs, so user defined types. And you might not really be aware of what the power of that is. And so I'm going to talk a little bit about what a type is for a second. And again, this is the very basic end. This live stream, we're going to go from the very basic up to some of the most advanced things that you can do on a Siemens processor, or at least get to where, the start of it. So the basics about a type is, if you notice on this, have I jammed up? Probably so. I've got a lot of stuff going, but if you notice here on this data type, those are like booleans, integers, reals, unsigned integers. And if you click on here, you can sit and say my tag 2, and if I hit tab, I can go over here and start typing in things. And here is all of the data types that are built in, that are available to this block. And you can see there's a lot, like bytes, booleans. We're going to talk about arrays here in a second. Characters, some stuff that may not make sense, like db any, but then there's other stuff that's like d words, dates, like all sorts of stuff. And those are types. And so those are data types. And eventually, if you are kind of used to programming in another language, you might understand what a struct is, a structure. And honestly, we go down here, I bet you we have this. Yeah, we do. We have a structure. We also have, we don't have it in here, but a structure, a UDT, and a PLC data type are essentially all the same thing. Now, you do have a struct, and they do have kind of differences, and we won't really go into them right now because it doesn't really matter, because we're going to talk about PLC data types. So all of these are kind of built into the system. They're just available in TIA Portal. They're what's called basic types. Now, a couple of things that we have down here is things that are either really interesting types here. So in the last live stream, we kind of talked about SIMATIC. We talked about the ability to be able to write parameters to a Dynamics drive directly without having to use a telegram. And we brought in what's over here. We brought in this SIMATIC block. And that SIMATIC block accidentally unbeknownst to us, actually imported a bunch of data types into the system data types. So we can see these over here. I'll show you where these show up in PLC Datatypes. All right, we know. We can go down here into system data types, and we see these data types that were actually brought in and imported when we drugged that SIMATIC block into our program. Now, one of the things that when we were talking about SIMATIC that I had got thrown off guard, because apparently they had changed the way SIMATIC worked. I was used to the SIMATIC S, and I've got a couple of shorts talking about that if you didn't show them, or if you haven't seen them. But one thing I didn't realize is that the new SIMATIC block has data types associated with it to make it more flexible and easier to use. So let's go and let's drag in this or a SIMATIC block. So I've had this collapse this whole time. So let's go to our instructions. Let's go to our optional packages, I believe, our Dynamics, and let's drag in our SIMATIC S that we struggled with last week. By we, I mean me. So again, when you bring in a function block, you will need what's called an instance block. And so SIMATIC instance DB. And we've talked about this when we've been talking about function blocks. And if you don't really know about function blocks and kind of what these instance DBs are, I encourage you to look up. I have an edited video that's specifically about OBs, FCs, and FBs, and it really tells about what's going on here. And if you're doing that, you got to go to my channel. So hit the subscribe button while you're there and ring that bell so that next time we go live, if you're watching this on demand, you get to participate live. So we're going to create and we're going to bring in this SIMATIC block. And one of the things that we got tripped up was this parameter block. And so one of the things that I want to show you is if you go, and this actually has a, when you import this block, there is a help file that you can get to that, we'll minimize this, that actually talks about what this parameter structure is. And I didn't realize when we were talking about it last time, I didn't realize this change. And so this parameter is of type SIMATIC. So what this does, and we'll go through, and what SIMATIC wants is a start would be how often you actually want to up and write these parameters. The read write, pretty simple. 0 means it's only reading the parameter. Write, or 1, write means it's going to write these parameters. Parameter number is the number of parameters that you are wanting to write. And then the access number is the hardware ID that we talked about. Sorry, not hardware ID. That is the drive object number in the SIMATIC block. If you're using a G120, that's always going to be drive object number 1. An S120, more complicated than that. We talked about that in the last live stream. That part I knew about. This is the part that I didn't, the PLC side. What are the odds? So this parameter instance is actually looking for an array of 1 through 16 of SIMATIC parameters. So I hover over the little line there, and it tells me what it's looking for. It tells me it's an in-out, and it's an array 1 through 16 of SIMATIC parameter. So let's do this. I'll show you how to actually make that data. So it wants one tag to connect there of type array. Okay. So not only, so let's do this. Let's do my parameter, or let's do my Dynamics, Dynamics parameters. So that's what we're wanting to do. and it's wanting an array of a certain type. Let's look at this for a second, and I want to look at this SINA parameter type, because what a parameter or what a custom data type does is you are able to define a structure inside of it. So think of a custom data type or a PLC data type as a mini data block, because the same way in a data block you can define, I want an int here, like I've done here. I want a Boolean, then an integer, then a real. You can do the same thing in a PLC data type. And we're going to go through in a second and talk about how to actually make your own custom type, because when we get to that sort of stuff, we're going to need it. But just know that when I imported that SINA para block, it imported this custom data type called SINA parameter. And that SINA parameter defines a couple of things. It defines a parameter number, index number, value, format, and an error ID. And those are the things that are associated with your parameters. So let's look at this. And again, all of this is in this help file. It's just a little bit more difficult to kind of talk through. And I'm going to step through essentially the information that is in this help file to help you understand how to associate not just make one video PLC to G1 using HMI. Yeah, so we did that control. We actually did a little bit of that in the last live stream, Rojan. If you go through, and unfortunately I haven't gone through and made the chapters. So I will make the chapters in the previous live stream about doing directly controlling and directly accessing a G120 just using an HMI. And so that's pretty cool. You actually don't even need a PLC to control a G120. You only need an HMI. And that was kind of in the last live stream. But what we're talking about here is being able to directly access the parameters like the HMI, like the trick that I did in the last live stream. You can do this with the PLC and directly access tags using this. So let's get back to going through and talking about what this SINA parameter structure is. And the parameter number is your G120 or S120 parameter. And so if you're wanting to say change parameter 10, why would you want to change parameter 10? Because that makes it to where you can change like motor data. So like parameter 300s are motor data. So the only way that you can change a parameter 300 parameter would be if P10 equals, I believe 3. I may be wrong. It might be 4, but it's going to be either 3 or 4. So parameter number 10 has to be something other than 0 in order to change configurations. So in that case, we would want to do a parameter number 10. Our index is the little number inside the bracket. It would be like parameter 10 doesn't have an index, but say for example, parameter, I think it's 2080 is the PZD. So the telegram information coming in, it's going to have indexes. So if you're wanting to modify those indexes, you have to put that index number here in parameter index. The value, there's two different values here. And if you notice, one is a real and the other is an integer. And so those are actually the only two types in a parameter. So if you have a Boolean value, you're going to put a dent. You're going to use this S value here, and you're going to set it equal to 1 or 0. And so that's how you're going to use that. Anything else, I think in the help files for the Dynamics parameters, it's not a reel, it's a float, but reels and floats are the same things. It's just floats are old school hardware guys call them floats. And then format and error number are defined in your help file here. Maybe it's not here. Yeah, so format of value. So there's a couple of different formatting values. So that is here, determined by the block itself. Yeah, so don't worry about that. Don't worry about the format and the error number, because the block itself is going to be modifying those. And so that's kind of statuses that you can look at. Now, so that is kind of how a PLC data type, or a UDT, user defined type, or structure. They're all kind of the same. Structure, UDT, PLC data type, all the same. That's how that's defined. Well, our block here wants a array. So an array is a built-in type. And the easiest array to think about would to be like an array of Booleans. So an array 0 through 7 of Booleans would be 1 byte of data. And then each array is going to have an index. Array 0 would be byte or bit 0 in our case, and then 1, 2, 3, 4, 5. Let me show you. Show you what I mean. Dramatic music change. So let's go through and go ahead and do what it's wanting, and we'll talk about this. So it's wanting an array. We can go ahead and click of SINA parameters, but it doesn't want 0 through 1. It wants 1 through 16. It wants 1 through 16 of SINA parameter. And when I hit this, it changes. So I'm going to go ahead and delete this single SINA parameter, because you'll see why. So I've created this array 1 through 16 of SINA parameter. Now, this array value is the starting index and the ending index, and it will fill out everything in between. And I'll show you here. So array 1 through 16 of SINA parameter has, if we add these up, hold on, escape. If we add up all of these, if I can actually do this, I'm wanting to select. If we add up all of these, this would be 16. So 1, 2, 3, 4, all the way up to 16. That's 16 instances of this data type SINA parameter. So each one of these has SINA parameter. Pretty cool, right? So that's an array. What's the difference? It started off with a 0 here, right? Well, what's a 0 to 16 of SINA parameter? Oh, it starts at 0 and then goes to 16. And if we count these, 0, 1, 2, 3, you notice you have an extra. So there's actually 17 instances of SINA parameter for this one. So that's a quick little thing, but makes a big difference. If you're trying to load memory like we're doing later, you want to make sure that if you want to load 16 bits into something, you either do 0 through 15 or do 1 through 16. Don't do 0 through 16, because then you're going to overlap, and that's going to be trouble. just to say the least. If you start overlapping in what we're doing later, you're going to be in trouble. So let's change this back, because we want 1 through 16, because we have to have 16 instances of this sign up parameter. So if you're on the stream now, go ahead and do me a favor and hit the like. We're going to be on here for probably another at least hour and a half or so talking about this, and so maybe we can get more people on, and that's the biggest way to help this channel, help get these videos out, is hitting the like button, commenting, and if you haven't already subscribed and you are watching this on demand, hit the subscribe, make sure notifications are on so that you could be on live the next time that we go live. But let's get a little drink. And let's move on to the next thing. Exactly, Lucid. It's for the algorithm. You know, when you're watching these YouTube videos, like I watch a lot of YouTube just because I have trouble going to sleep at night, and until you start making YouTube content, you don't realize how much and how important those little things are. And so, yeah, no, we don't want to go to that. We want to go to this, the algorithm. So now we are wanting this to put our tag that we've mated. Yes, I'm from Alabama. If you're not from the U.S. and you don't know what that reference is because I'm from Alabama, I get to use words like mated. But we are wanting to use this tag that we just made. So my Synamics parameters. So this array 1 through 16 of sign up parameters that this block is wanting, we want to access this. And so a couple of ways that we could do this is we could kind of undock this and drag this over into our, like that. We could do it that way. And why it looks like that, who knows? Maybe it's just not compiled, but we could do it that way. Or, oh yeah, because this block has not been compiled. That's interesting to show. So that is interesting. So this block, remember we turned off optimized block access. And so one of the things about unoptimized blocks is technically the offsets of the parameters are not created until you've compiled the block. Now, what's an offset, you might say? Well, very important later, but let's just go through and click in here, and then we're going to click compile, and it's going to compile this block, and now we have offsets. And that's very important later. But one of the things that you'll also see is now this thing over here knows that this sign up parameter block, it knows where that my Synamics parameters is actually located. So how do we use this? Well, first of all, we're going to bring that back in, then we're going to minimize it. So how do we use this block? Well, one way that we could do is we're wanting a to access one specific parameter set in this my parameter. So if we bring up this block, we're wanting to access, say, this first parameter set. We want to change P10, right? That's the first thing we want to do. We want to change P10. So we want to set up each individual piece of that. So we can go in and use move blocks. Okay. And we want to move a 10. into, we're going to go to, and again, these are symbolic. And so we can, we're going to use the symbol for this. And again, DataBlocks automatically create these symbols, these tags that you're used to. And so you go mydb dot my Dynamics parameters, and then we want to pick the index. So we know index 1 is that, and we want to change the value. No, sorry. We want to change the parameter number. Unsigned index. Unsigned in. So we want to do that. We want to go through and we want to change. We want to put a 10 into that first para number. Okay. And then say we want to change P10 to, undo that. Say we want to change P10 to, Control C, Control V. Now we want to put a 3 in there. And that's not going to be, we want that into actual, we want to put a value in there, right? And in order to do this, we would need to set this to a write. Pretty simple, right? So pretty simple after you get everything set up. And that's how you use this SIMATIC block. Now, there's a lot more into it that it took a little bit of understanding. It took an understanding of not only the fact that you're using a PLC defined type, or a PLC type, PLC data type. I will eventually get it right, I promise. But then you also have to use an array. Now, that's for that specific SIMATIC block. If you have any questions about that and you're on with us live right now, go through and yeah, just ask that question. Ask a question about anything that we're talking about, and I'll try to go through it in a little bit more detail. So I'm going to shift in the meantime to kind of show you. This was a predefined type that when we brought in this SIMATIC block, it automatically brought in this data type, this SIMATIC, and a lot of other stuff too. So I want to go through and show you kind of the rabbit hole this can lead down into, because one of the things about array indexes, so I have this SIMATIC type, okay? And let's look at this index. It is a data type, SIMATIC. It has some stuff. Now, inside here, these are all standard data types. So unsigned integers, reals, double integers, bytes, words, that sort of stuff. Here's where we can get a little bit more complicated. I'm going to show you an actual program that I have that I wrote, and I wrote it a while ago. And so I've noticed that that it doesn't follow some of the rules that I've set for myself, but it goes through and really shows how deep the rabbit hole can go when you start using PLC data types and these UDTs, structures. You start defining essentially data blocks. And then, so let's just step through this cycle storage DB. You don't really have to know what it is, but this is it's a machine that controls a bunch of valves in order to produce, to go through and wash a keg, or wash a piece of brewery again. It's in a brewery, beer, and they're washing stuff, kegs, cystals, like all sorts of equipment. And this program goes through and essentially needs to, in sequence, set up a bunch of different valves. Some valves are on sometimes, some valves are off, and it reconfigures everything to where each different time as it goes through, it has a different valve configuration, and then it switches to the next valve configuration, does some stuff, switches to the next valve configuration, goes from there. So the thing about it is we have this cycle storage DB, and it's just an array. It has 10 instances of this ABW cycle. So pretty simple, very similar to what we did there with the assign a parameter. We've got an array of this PLC defined type called ABW cycle, and I defined it. And here's where it gets a little crazy, because unlike in our assign a parameter block or assign a parameter data type array that we want, this one is not nearly as simple. It's not an array of a data type that has like standard data types. Starting off, you can see that this is about to get confusing. So this ABW cycle is actually an array of steps. And so this step, this ABW cycle type, is actually a step that has 32 of these step config types. So we go into this array and we see, okay, it's getting deep. So this is an array in an array. And this type is just an array. Yeah, it confuses me when I'm thinking back. And honestly, what we are doing later on in this episode, or in this live stream, may actually be able to simplify this type. But I'll show you why this is necessary. So this first step, and think about it, you're going to take step 1 is a valve configuration, and it's going to do some stuff. And then you're going to go to the next step, and it's going to reconfigure, and then it's going to do some other stuff. And then step 2, same thing over and over and over again. Well, these step configs, again, is a user-defined type. So I went through and defined it. And so let's look at what that type is. Oh my goodness. Okay, so we've got Booleans, times, Booleans. We got some stuff in there. But we also have another UDT, another PLC defined type, a type inside a type. So a UDT inside a UDT. And so we're getting these like layer upon layer upon layer of depth into this. And so now these valve configs, fortunately, is just a bunch of different types, or a bunch of Booleans for the most part. Now, in this case, we've named the valves. So our tap water valve, our hot water drain valve, our hot water fill valve, caustic drain, blah, 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 all of this. And then the tank is an actual variable, a variable valve. And so that integer is 0 to 100, which is actually can do that. So we notice this pump config, same thing. Fortunately, all of them are basically the same thing. They are solenoids and pumps that are just Booleans for the most part, and then a couple of time, because we have some timers that we're going to be using. Now, how do we use this? So the reason why it gets so kind of like confusing is each step has a bunch of valve configurations, and every valve configuration has 1, 2, 3, 4, 5, 6, 7, 8 valves. So every valve configuration has 8. Is that 8? Did I just count that? Yeah. So 8 valves. So every valve configuration has 8 valves, but every step has more than just a valve configuration. It has pump configuration. It has some starting, ending delay times. It has some things that are like, hey, do I want to wait for an actual user input in order to continue on to the next step? So the valve configuration has 8 valves. Each step contains not just the valves down here, that valve configuration, but it also contains other stuff, which contains other stuff. So, and what makes this particular one so kind of annoying is I gave the end user, I wanted them to be able to configure their own valve configurations. I wanted them to make their own cycles. And so in order to store the cycle, one cycle is going to be a collection of steps. And then you want to store multiple cycles. So that's what's going on here. So each step has multiple entries. Some of those entries have multiple entries. And so each step, so you have up to 32 steps per cycle. And then you have up to 10 cycles. So 10 sets of steps. So how do you use this stuff? Well, it all has to do with that index. And so let's go through and look at, which, by the way, I technically have one instance of Portal open. And if you're not familiar with this, these reference projects, you can open a reference project and not have to open 2 instances of Portal. And so this is a keg washer program. This is a totally different plant program. Excuse me. The way you get these reference projects is if you don't have this option, you go to View and then Reference Projects, or just hit Control 9 and it brings up the reference project screen. And then you can go and click Open, and then you just open either an archive or an actual project file, and it will open up that to where you can actually open. So what I'm going to do here, I believe it is, I want to say it's machine cycle control. It's been like 4 years since I've, no. So let's see, because I want to go to, maybe it's just, let's just dig through it. The OB1 has this, that's all of that. Yeah, so it's machine cycle control. And what you're doing is, as you're going through, is you have an index. Here it is. So this is index increment conditions, because what you have here in this code is a PLC in its static. It has an index that, as this is going through, which, here's a problem with this machine. It's not just one pump washing station. You have 2 pump washing stations, and they each individually can be running. So you have 2 instances. So you have to have this in a function block to where you can actually run 2 different instances at the same time. So this is really kind of complicated. It's overcomplicated, but you have this index, and essentially what you're going to be doing is incrementing this index through the steps. And so if you look at this little tag here, it's kind of hard to see, but you have current machine cycle, which gets passed in from the outside when you actually set on the HMI. So cycle storage dot machine cycle, then you have an index. And normally this index would look something like, let me swap over to this real quick. And then move this down here, because this is pretty important in being able to how's that not swapping over? Hold up one second, let me get a pen going. Okay, for some reason it's not going to work. But so let's just do it this way then. Didn't want to write over this, so let's write over this. So normally you would have a machine cycle, and inside your index you would have a number like that. But what we have, make sure that I've got everything going. So let's just do no cam. So you would have machine cycle node number, and then you'd have dot step, a number, and then your actual tag that you're wanting to pull out. So that's kind of the structure, because you have your first array and then an index, your second array, because every one of this machine cycle has multiple steps, and then you want your step number. This is an index, and then this is your actual data, like that. And what we have here though is machine cycle, and then it has a tag. So this is a variable. Like that. Dot step. We have another tag. And that's a variable. And then the data that we're actually wanting, dot tag. Okay, that's what we're wanting. But that's how we dig through this. Now, because both of these are set somehow programmatically, because both of those are set programmatically, we're going to go through and have code that increases this as we go along. So we're going to have this, we'll call this v bar index 2. We're going to have this to be 0, do some stuff, then increase it to 1, do some stuff, increase it to 2, do some stuff, 3. And then eventually, somewhere, we're going to be like, hey, when's the end of all these steps? And we're going to get to the end, and then we're going to stop. So show you kind of how that is, show you how that goes here. So with this is what we were talking about here. So we're wanting to modify or to use on this timer, our in delay timer. Okay. So this index, so we have current machine cycle is passed into this function block, but it is actually set from the HMI. So the user on this one goes in and says, hey, I want to run cycle 1. So I want to run cycle 1 on this, and then the program steps through the indexes. So what does Lucid say? So the index points to an array number that contains parameters for the function to be called. Yeah, that's the index points to an array number that contains parameters for the function to be called. Yes, that's right. And because this inside of here, you are because all of this is variable, those values can change based on where you are in the array. And so in essence, that's what you're doing there, Lucid. It's not necessarily passing different parameter numbers. It's the program is looking at a different point in the array. So when you're going along, the first set of parameters, it's not that it's just looking at different places. So it's not necessarily passing them different parameters. The program is just designed to look at a different point in the array. And that's really going to get into where we're getting at. And I brought this program up before, and I called it baby indirect addressing, because you're creating arrays and then using the index of the array. And so it's pretty well structured because this data block has these arrays already in it, and the array information is defined. And so this data block is not unoptimized. So this is optimized so it doesn't have these offsets, but we'll get into a little bit more with that in the most advanced portion of it, Lucid, because this is what you've been asking for a while, and we gotta step up to it. So instead of just, this program is designed to just go through and look at first, it's going to look at step 0's value, and then it's going to look at step 1 just by incrementing that step number index. And then you could technically skip. You could go all the way down to step 5 and it would skip. And these array indexes contain essentially how much data is actually here. Now this actually contains a good bit of data. So one step actually contains a decent amount of data. And it's all kind of collapsed into this one array index. This step index 5 contains all this data. So not to reiterate on that, if you have some questions about kind of like what that is, feel free to jump in if you're on here live. If you are catching it on demand, feel free to comment a question, and I'll try to keep up with them. The channel's not big enough now to where I can't keep up with comments, so you, as an early adopter, you get the privilege of being seen. I doubt that a pretty dry technical content page like this will ever get big enough to where I can't keep up with the comments. But yeah, if you have a question, you're watching on demand, feel free to comment. I will go through and answer them. And if it's something I can't answer in text very well, well, I'll talk about in the next live stream. So that's a way that even if you're watching on demand, you get to participate, because it might determine what I go through next. So that's pretty much it right there for arrays. Arrays have indexes, and each index can have multiple layers. So that is arrays, and that program was fairly confusing, and we are sitting at 1 hour, which is perfect timing. So if you've made it this far and you've been watching for the full hour, kudos to you. Either someone's forcing you to watch it, or I don't know, maybe you're on your lunch break at work and you're just taking Friday, and your boss is like, hey, as long as you're learning something, that's good. Well, guess what? Hopefully you're learning something. I gotta take a break, mentally make a shift into this, because we're about to start talking about probably the most complicated topic that you can talk about in all of Siemens PLC programming. And the music fits the drama, because I'm not just being dramatic. This stuff can make or break you. And one of the things that I don't know why, well, I do know why, because a little history lesson. Back in, I guess when PLCs and kind of automation was kind of started coming into plants and factories and things, you had computers, and this was back like in the 80s. And to think about how long ago the 80s were right now is really depressing. And yeah, F in chat for pay respects to all of us 80s people. I wasn't around, fortunately. I mean, I was alive for some of it, but I wasn't programming when I was like 2 or 3. But back in the 80s, essentially all you had were embedded systems, and like embedded systems writing in assembly language and programming in kind of like very difficult to understand methods of programming. You were really having to worry about like clock cycles, and oh, hey, in order to set up a timer, you would literally have to know how fast your crystal on your processor was running, and just complicated. But that was the only way. I mean, it was the dawn of kind of technology, and as this technology started to go into plant floors, and people are like, hey, I want to be able to automate things. I want to be able to turn on and off these valves. I want to be able to do all this stuff. Well, it got to where there was kind of a break in methodologies and thought process. And really it boiled down to where Allen Bradley made their name was creating this kind of language called ladder logic that, and I'm not meaning this from like a like intellectual standpoint, but it really simplified the way that you could write these programs. And so when Allen Bradley came out with essentially a processor that used ladder logic back in the 80s, it really changed the game. And it created this kind of system to where a less technical person, you still had to be very technical in order to program in ladder logic. And let's not belittle automation engineers in any way, and Allen Bradley made it easier to access this technology, because before you had to have a very special mindset in order to get to this. And so Allen Bradley created ladder logic, and it simplified the way that you could do simple projects and simple things. Because most of the time, like especially in the 80s, most people, all that they were wanting to do was turn on and off valves, turn on and off relays, turn on and off like lights, and like really bit level, just, hey, I want to turn something on, I want to turn it off. They weren't doing calculations, they weren't doing a lot of stuff. It was, hey, if this comes on, turn this on. If this goes off, turn this on. If this, very simple. And ladder logic does that extremely well. Where ladder logic starts to fall off is when you start working with complex data. It starts to lose its ability to do, because its main purpose of ladder logic is to make things easy to access, easy to program, easy to get to. Whereas it falls short when you start dealing with complicated things. And let's be real, it's not intended to be, ladder logic is not intended to do complicated things. It can absolutely do complicated things, but there are usually better ways. Once you start getting into complex math equations and like that, there's better ways of doing stuff. One of the ways, or one of the things that ladder logic doesn't really do very well, or at least is, it abstracts away memory. And we've been talking all day about memory. And one of the things that kind of Alan Bradley does, and we talked about it before, is abstract away where your tags are actually connecting into in memory. And it makes things very easy to access and easy to program. But then there's some things that happen that you can't end up doing very easily because it's easier to do something over here, and that sacrifices this complicated thing. And sometimes, actually, usually, complicated things are complicated. Duh. Groundbreaking. But what we're going to be talking about is a concept called indirect addressing and using pointers. And it is really an embedded system topic. It really goes back to the 80s in the kind of thought process and what it's doing. And you might for a second think, like, well, why would I want to go back into the 80s? Why would I want to go back to that sort of technology to be able to do something? There has to be a better way to do it. And for like 90% of applications, yeah, that's completely correct. Especially most people are not working in places that would really take advantage of doing this type of programming and working with this type, because you're most likely either working at a plant or a factory that has some equipment that has come to you in some shape, form, or fashion, and you might want to add on a feature to it, like an alarm or a light or an LED, like some small feature. You want to add in, say, a curtain, a gate, like an automatic curtain or something, and you're just wanting to add a solenoid output. And so you're not going to use indirect addressing and pointers and all this stuff that we're about to talk in order to do that. You're going to make a little block and then grab some memory, grab some IO, and then do your thing. But you may notice, especially if you have gotten your piece of equipment from a large OEM that does a lot of production, say for example, like a Danieli, which is a big steel OEM. They do a lot of work in steel. You may have like a WIA press or something, and these are very large non-US based OEMs. You'll get like presses that come from large European OEMs that like the program is all written in indirect addressing. A lot of tier suppliers for Mercedes. For those of you that are either in an area around a Mercedes plant or around, like in Europe, I'm not sure where all the Mercedes plants are across the world, but just so happens the only one in the United States is in Tuscaloosa, Alabama. Roll Tide. And because of that, a lot of the equipment that is in the area comes in from these German OEMs because of the German connection there. And it's written in these kind of indirect addressing. And you're like, oh, the Germans just want to be complicated. That's just what Siemens people do. And let's be real. Siemens has had ladder logic for decades. They've had it since the early 90s. And still, most or a lot of German programs that come from Germany still are written in these other languages. They're not written in ladder logic. So it gets this reputation that, oh, Germans, particularly Europeans, don't like using ladder. They don't like using these things. They want to be complicated. Well, the thing about it is the reason these programs are written this way isn't because they want to be complicated. It's actually to the original manufacturer, the OEM of the equipment. It makes things a lot easier because they write one complicated block one time and then drag that block in and hook it up. And the methodology behind their thought is instead of creating a program that is that I have to program for each piece of equipment, well, they are making equipment that is 90% the same. And then the only difference might be a couple of options or modifications that they have on their cell or feature or whatever. And so they're like, all right, I'm going to write this block so that I can reuse it. And it almost gets down to, in some of these things, to where you have what's called utility blocks, where you have a block that does one thing really well, and that's it. Well, it does this thing, and it connects up, and you have to use this other block, and it connects to this block, and it connects up to this block. And essentially, you're only having to program in just a very few amount of things, and you just drag a bunch of blocks in, and it works, and it runs. Crazy thing about it is, using this indirect addressing, you can create programs that aren't even really programmed. You just configure them. You load one software load onto your program, and then you can configure the IO. Because just like in my little keg washer program, you can go through and say, hey, I want these different valve configurations. I want these different things for each cycle, each step of the way. And I'm gonna, as I go through, I'm gonna change through them. Well, you can take that to the next level. Now, my program, the reason I called it baby indirect addressing is because still technically everything is fixed. It's all in arrays. It's fixed in memory. Well, with true indirect addressing, you're just pointing to memory locations. And here's where this gets into this, like the real technical talk. And I'm going to go through, and this is really combines some of my experience in electrical engineering and computer architecture, which not many people have. And so this is going to go into a lot of like memory structures and a lot of really deep concepts. And the thing about it is, if you don't have a good understanding of how memory works, then you're probably going to run into trouble if you were starting to use pointers. So I understand it enough to talk about it. And I'll be honest with you, from a technical standpoint, I just learned how to execute these concepts this week. I don't know if you saw the community post with the whole watch and like me channeling my inner Bruce Lee and all this stuff. But I'm 37 years old at this point, and it's a little bit difficult for me to learn like complex new things. And this week I went through and actually had to implement some of these things, and I'm going to show you how they were implemented. And hopefully this gets you enough started to where you can start trying to play with these concepts in your mind. I will say a word of advice before you start programming in this and attempting to run a machine with this type of information. You really need to understand what you're doing, because I'll tell you, I'll show you here in a second why, but you can really run into trouble really fast. So let's, I'm gonna kill this monitor. Oh gosh. I'm trying to make it to where I can be heard. So let's swap over to the sketch pad again. And I'm going to keep my face up here. And so I'm going to remember, and I'm going to come all the way over here. Am I here? Am I here? Okay, I'm going to do Control A. I'm going to delete all this, clear my screen, and we're going to talk about memory. And so every processor, and this isn't just a PLC or Siemens, anything. This is any processor. So this is like computer architecture 098. It's like the very basic that you need to understand about computer architecture and memory. Every processor has memory locations and is broken up into its constituent pieces. Now, in this case, we're going to call this a word. Okay? And we've kind of talked about this sort of stuff before. And that goes on and on and on. But in programming, in digital logic, you have Booleans, and those look like E's. That is terrible. That's Booleans equals a bit. And so that's 0 or 1. Our basic this is 0 or 1. And if you collect up 2, 4, 8, 1, 2, 3, 4, 5, 6, 7, 8. You collect up 8 bits, you get a byte. I don't know why I put that there. Okay. So Boolean is a bit. 8 bits is a byte. You put 2 bytes together, you get a word for us, because we have a 16-bit word. Okay? And so that means 8 bits in a byte, 8 bits in a byte, and 16 bits in a word. And then you can go D word you actually get 2 of these. And so that's 32 bits. And then that equals 4 bytes. Okay? And that's important to know, because what we're going to be talking about is actual memory. And when we are looking at this word, we can actually think about some of these being split up, okay, into bytes. And so byte and then byte. Okay, so this is kind of like basics of digital logic, memory addressing, and all of this stuff. And I'm sorry that I have to assume that you know nothing. You may know all of this, but this is how all data is stored on any processor. And a real takes up 4 bytes. So a real value has a certain, what's called encoding. It's a certain structure of bits to be able to talk about, or to talk. So for example, a Boolean equals 1 bit. And here's just a quick difference between Allen Bradley and Siemens. A Boolean in Siemens equals 1 bit. A Boolean in Allen Bradley takes up 32 bits, because that is, Allen Bradley uses a 32-bit word, so its base allocation is 32 bits on its tags. And so 1 Boolean is 32 bits. So obviously, if you're using a lot of Booleans and you're using a lot of digital logic, you're going to eat up a ton of space in an Allen Bradley processor. Just because every Boolean takes up 32 bits on an Allen Bradley processor, every Boolean on a Siemens processor takes up 1 bit. And so you can do, it's literally 32 times bigger just because of like Boolean. Now, if you're using a lot of real data and like real integers and stuff, the program sizes are going to work out to be about the same. But you'll find out that a lot of your data is actually in these smaller bits and byte formats that you're using. And so if you ever compare memory sizes between Allen Bradley and Siemens processors have a lot less memory, and you're like, holy crap, like these aren't as capable, I can't do as much. But in fact, you probably can do more with a 10 meg a 10 meg whatever than you could do with like 100 meg from Allen Bradley. So anyway, all that to say, getting back to this, not getting distracted, that you really need to understand this concept that a byte is a collection of bits and words are collections of bytes, and get kind of used to this kind of like structure here. Now I'm going to delete this from the screen, and we're going to go back to our little memory, and I will redraw these little bytes because it's important for you to see this. So get a nice little picture in your mind, and gone. So let's draw. We're going to split this in half. And just so it reminds you that word is our base memory place, and our word is 2 bytes. It's gonna matter. So this is how all the memory on a PLC is broken up. Well, what you have is essentially there's a thing called a pointer. And I realize what I have done. I have my face there. So much better. Word, byte. Now you can actually see all the stuff I've been talking about. So, so a word is 2 bytes, and this is how all the memory structure in any PLC, in any processor, in anything is broken up. So you have what's called a pointer, and I'm gonna blow your mind here, but a pointer points to memory. It's crazy. Yep, I know. All right, dream over. No, but for real, what a pointer does is it, instead of actually containing the data in here, say that in this little section right here, let's go back to this. Say that in this little section right here, I have a value of hex FA01, some random number. And if you don't know what hex is, you got to look up different numeral representations, but just know that that's a number. It's just represented in a different format if you're not familiar with what this is. Now, one thing about this though is, before I go too far, each one of these addresses, so each one of these little blocks here, so like where it says word, is going to have an address. And for this, we'll make it simple. And again, 0x means hex. So hex representation 1, hex 02, 0 hex 03, 0 hex 04, on and on and on. Okay, so we have right now, we have this value, this pink value here, that at the memory location hex 3, at the memory location hex 3, we just have the actual value, a number, FA01. So that value is whatever it is. That's a number. Well, it's at the memory location of hex 03. All right. So a pointer, if we wanted a pointer would not, it would not contain 0 hex. It would not. So it would not contain the actual value. Instead, it would contain the value 0x, in this case 03. And I have wonderful handwriting. So it is not storing the data, it is pointing to a location. So it is pointing to an address. Okay? So a pointer only contains an address. It does not contain the actual data. Well, this is very similar to an index in an array, right? So that index doesn't contain the actual data. It just tells you where to go to get the data. It's pretty cool, right? So that's why arrays are baby pointers. So an index in an array is a baby pointer because it's a very restricted pointer, because an array is defined. Well, the thing about pointers in Siemens is they can point to an area. And the way you start to use them, and the reason you would want to use them, is that you want to, like in our keg washer program, you want to write a program that the stuff inside the data can change, but your program does not. So you want to write a program that even if this stuff changes, then your program does not change. And it's kind of mind-blowing, but you can actually write programs using indirect addressing, referencing data that doesn't even exist yet. And what I mean by that is your program can actually be programmed to write stuff that the data blocks are written in real time. So, and the way it does it is you are allocating a section of this program, and then your program points to the start of that. And there's nothing in here. And if you're not, I'm writing null. When it's compiled, there's nothing in there when the program's compiled and downloaded. But then once it starts running, then all of a sudden it starts filling in stuff and actually allocates out this. But this pointer never changes. Like, the pointer's already there. The pointer is compiled in. So that's what a pointer is. Very, very deep. Very deep. That's why I had to put on the suit, because I had to step it up. I had to step it up today, because we're becoming real programmers. And, well, I guess real programmers like sit in a dark room like I'm in late at night and drink Monsters and have Cheetos. I don't have Cheetos. I have some cashews over there. But anyway, getting back to what we're going to do with pointers. So what we want to be able to do with a pointer is we want to be able to say, hey, I don't know, my program doesn't know where at the time when I compile it. So when you compile it, you can sit there and say, okay, you can define an array size, for example. And that's why an array is restricted. It's defined. Well, you can actually go through and make a variable length data block. So your data block can change sizes, and we're definitely not getting into how that is, but you have to be able to use pointers on that. So what I have a program that we're going to talk about, that we're going to get into. And so for a minute, let's talk about this program. Let's get this swapped over to that. And we're going to bring up this other thing up here. And I'm going to delete these too. Well, I'll just leave this here. So at its core, what I'm wanting to create is a end user defined configuration. So I'm not having to program in everything into a specific processor load. And you might be able to see what this is. It's the start of a batch control thing, and I don't mind showing you it because it's not completed. This is just the very core part of how it actually goes through and handles the memory. Because what I'm wanting to be able to do is have this same program be able to run a program that has 4 ingredients or 400 ingredients, all running off different feeders, and all of them have different configurations, and all of them have different material properties and flow rates and densities and like all this stuff. And so in order to do that, I either have to write out a program that says up to 400, and then if I have one that's 4, I have a way overkill program that's going to have a processor that has the ability to handle 400 and really only need 4. And that's going to make my system too expensive for the guy that only wants 4. Because the guy that only is mixing 4 ingredients does not have nearly the amount of money or that someone that is mixing 400 ingredients. So in order for to write one program that controls both and can scale up and down, I have to sit and make it to where this data block, if there's only 4, it's this big. If it's 400, it's this big. It's huge. And it handles the data efficiently no matter what. So what I've done is I have created a data type that is called ag batch bin. So this is all of the data that up front I think that I'm going to need to be able to go through and do these kind of batching process. And if you don't know what batching is, it's taking and mixing. You take materials in these bins and you say, hey, I want 5 pounds of flour, 5 pounds of corn, 5 pounds of this, and then 100 pounds of potash or whatever, like these different ingredients, and you're weighing out different things. And it's just like mixing bowl. I mean, it's a recipe. I mean, just like a recipe in your kitchen, you got a recipe in a feed mill or in a fertilizer plant or whatever. And that's what this is doing. Each bin has to, I'm just going through and I've created this fairly complex data type, and it just so happens to have 64 bytes of data available. And so you'll notice that I have things like spares, spare 5, 6, 7. I have a spare int here, a spare real, because base 2 numbers really matter. And if you don't know what a base 2 number is, that's a Boolean, or a bit can only have 2 values. So you have 2 states. So every bit you add in adds a power of 2. Whereas we're used to base 10 numbers, like 10, 100, 1,000. Those are all base 10 numbers. Base 2 numbers are 0. So 1, 2, 4, 8, 16, 32, 64, 128, 2, on and on and on. And you're just multiplying by 2 each time. And so everything in memory and in computer architecture and all of that is all base 2, because you can only turn a transistor on or off. And that's the only 2 states that a physical silicon based transistor can have. Now, quantum computing, that's another thing, but we're not there yet. That's when AI will take over the world and kill us all and all that. So, but anyway, so I've got 64 bytes of data here, and it's got a bunch of stuff that I might want to use. Okay. And some spares, so that if I figure out later that, oh, hey, I want to add in this, I've got a little spare data here. So I've got this ag batch bin. Just know that it's got stuff in it that's important to my batch control. Well, this batch bin data, DB1, right now it's a fixed size, and in it has 2 things. It has the number of bins that are in the system as a value. Okay. And what you can do is that can be a user programmed value. So, and that's going to be important, because we're going to come in and we're going to look at that value and be like, check against how big this data block actually is. Because with pointers and indirect addressing, you can absolutely access anything. This is, they trust that you know what you're doing. And this can get you into a ton of trouble, because if you're off by 1 byte in some of this stuff, you'll start overlapping and overlapping, and you're going to be doing shifts, and you're going to be making like offsets and all this stuff, and you're going to shift and shift and shift, and then all of a sudden you're going to be writing into other values. You're going to be writing into like just other variables, other data blocks. Like, it can get crazy because it doesn't care. It's going to say you're going to start at one place, go to another. Goodness, we're an hour and 45 in. I gotta speed up. All right, so we've got our bins, which are arrays, and just know that this is an array, okay? And so each one of these bins has an index. And so I would technically be able to go through bins. I'd be able to go bins.1 or .bins1 .whatever, and I could access it that way. But the problem is I would need to know up front where that is and how big this block is, which I could do with this. But the thing about it is eventually this is not going to be a fixed size data block. It is actually going to be created after, like it is going to be created in real time. So it's going to take a configuration file that gets loaded in from the HMI. It's going to actually create the configuration for this system, and you're not actually going to program anything. So the only way you could do that is by doing indirect addressing. So you notice this block, unlike the other block, has offsets. So this block, this DB1, is unoptimized. So if we, just to reiterate, if you're joining in late, we're going to go batch bin data, right click, click properties. We have unchecked this optimize block access because you can't do indirect addressing with optimized block access. Which, by the way, everything that we're doing today, you can do on a 300 or 400 processor. We're using some data types that are available on the 300s and 400s. You just might not, actually, no, I'm using a legacy function that's available on 300 and 400. So you would be able to run this concept and this data or process that we're doing today, you'd be able to do it on your 300 processor, even in SIMATIC Manager. So step 7, V55 or whatever, 5.6. So, but in Portal, you have to uncheck this optimized block access. We hit that, and that gives us these offsets. Now, obviously, I have compiled this block, and so all of these offsets are there. So you can see that each block takes up 64 bytes. So 66 minus 2 is 64 bytes. And remember, these offsets always in bytes. Even though they show .0 here, from this outside, and I think there is some way that you might be able to change this, and like everything that we're talking about today is going to be in byte access, okay? Because we're going to be taking big groups of data and we're going to be moving around kind of like whole bytes or words, okay? So we look at this, and individually you can see these offsets inside here as well. Like that data type that I just showed you, that batch bin data, we have an array of, in this one, 150. I have 150 of these, and one of the things that we're going to go through now is we're going to look at how to access this using a pointer. So let's pull up this, and I don't know if you're on here, Lucid, but here you go. It's SCL. And if you're not familiar with what SCL is, it may change your life, because you may be more familiar with working with a text-based language like Python, C++, C#, Java, like any of these text-based languages. Well, SCL is available inside Portal, and I mean it's also available in on your 300 and 400 processors. So SIMATIC Manager, step 7 V56, it's available there as well. And so everything that we're doing here actually works because we're using compatible function blocks with the 300s and 400s. So you would be able to use this SCL code in SIMATIC Manager. Now, let's talk about SCL for a minute. First of all, one of the cool things in Portal that you can't do in SIMATIC Manager is you can actually do what's called inline SCL. This ag batch control function block is actually written in ladder logic. So we have networks, and I have all of these things that I've just kind of mentally went through, and I'm like stepping through all the ladders. This is a ladder logic, and then I made a network that is written in SCL. And the reason why you want to do this is what I tell you at the very beginning. Ladder logic is really great for digital control. If you want to do something complicated, like some sort of like complicated calculations, math is really easy in SCL because you can just type it out. I'll show you an example of this. Here I am calculating the total runtime on line 25 here. And you see that? Yeah. So I'm calculating the total runtime here, and it's just natural code. Like I'm using a round function, and then I just do my math like I normally would. Here's my variables like I would normally call. So you see the hashtag. These are all declared up in my interface as static variables. You don't have to do that. You can actually declare them in SCL, by the way. But here I've declared all of these things because I want to be able to use them in my ladder logic as well. So here's a thing to where I'm just taking and doing some conversions, and I'm trying to get a weight. I'm trying to get a weight that is being passed to me as target weight. And I've got some parameters that we're going to talk about how I've pulled them out of that data block. And so my bulk density and my rated flow, I'm dividing those out, fixing my units, and I divide it by, or I guess I divide that into my target weight, and I get the number of, I guess I get the number of seconds that it's going to take, and then I multiply that by 1,000, and I get the milliseconds, and then I round that, and that is the total runtime. And this total runtime is a S7 time. So total runtime here is a time value, and so those are in milliseconds. And so yeah, so here we go. Math is really easy in SCL. Also, you can only do these pointer functions in SCL. I tried to do it in ladder by using like move blocks and stuff, and you can't access the pointers in ladder. So you have to use SCL in order to do these pointers. I guess you can also use STL, but if you know what STL is and you use it, why? Why? No. So SCL is assembly language, and it is the original language. The only way that you could do it, could write PLC logic, and it is painful. Yeah, I'm not even gonna get into it. It's traumatic. By the way, that's the first program I ever wrote as like a kid. Whenever I was writing the program, was in assembly language. So that's why I'm weird. Don't be weird. Use SCL. All of that to say, let's talk about what a pointer is, because it's complicated. Duh. So we have talked about, let's bring up the help file. And we're going to bring it down here. Whew, maybe we're not. We've talked about these pointers down here on our sketchpad, right? Talked about this stuff. So a pointer contains some, it does not contain the information. It contains an address. No info, only only address. Like that. See? So, like, no info, only address. See it? See it? See it? No info, only address. Now, let's talk about a pointer type in, like, what the type is, because we want to declare a pointer, so we have to have a type, right? We have to have some sort of information. Let's go back over to our this one here. No, this one here. Let's go back over into our logic. So we have this input and output that we see. We have this input here called batch bin data. That is what that's what we're actually bringing in. And my dad wrote a little document about this, and I kind of chuckle at the way he did it. And the warning that I gave before was talking about how you can kind of get yourself into trouble. And the type, so the type that we have here, the data type, is the data type of any. And the way my dad describes it is kind of funny. He said in his little document that he put out that the any type should trigger into your head that anything can happen. And that should scare you, because if you notice, this is an any type here. And if we hover over this, it basically says, hey, you can put, if we hover over it, you can put anything you want. Anything that's possible, you can link in here. Do with it what you want, because it's a pointer. And let's look at the actual help file and the description on this any pointer, because it's more than just a single address. It does contain some information, but it does not contain any information about the actual thing it's pointing to. Let's go through this, and let's see if I can do something. Let's see. Let me get this pulled up so I can write. So we're gonna clear out Sketchpad. We're gonna put me up here, and then we are going to clear this. All that stuff's gone, and then we're going to bring this down here. Thought we were. Is that big enough to where y'all can see it? May need to zoom in a little bit. Let's do this. Make that a little bigger. Yeah, that works. Oh, that's probably gonna kill my computer. All right. So we are going to talk about this pointer, because this data type any actually does contain, is that, whoa, that's weird. Maybe we can't do this. I'm gonna have to hold up 1 second. A sketchpad doesn't like it being zoomed in. So, sorry. Yep. So let's talk about this this data type any here. So what we are looking at, and I guess it contains actual 10 bytes of data. So just like a real value, a real data type contains 4 bytes, an any data type is 10 bytes of data. And so I may have to be swapping back and forth between these screens. But the description of these is in this, you have the DB number. So think of this as, let me clear this. So think of this DB number as okay. So the DB number, where it's pointing to, and there's different ways, but for right now, we're just going to talk about DBs. You can actually point to like input addresses. You can point to all sorts of different things. But just for right now, we're pointing to a DB. And so this is going to contain the DB number. It's going to contain the offset of how much. So we're going to talk about these bottom things down here because that's where the offset is. So we've talked about a pointer before, like when you use like a get function, you do pointer. This would be for like a get. If you haven't watched my video on, let's see, it would be the DP read data and DP write data, which is the cyclic communication for Profibus. Watch that because we talk about these pointers. But a pointer, this type of pointer contains a DB number. In this case, it would be DB1. Some way to signify what type of data that you are pointing to. In this case, we'll point to a byte. So, or we'll do DBX. We'll point to the first bit. So the very first thing, DBX 0.0. That's the first place that it's pointing to. And then how much data you're wanting the pointer to contain. Okay. And then, so if we wanted 10 bytes of data, we would do byte 10. But in this case, we're actually wanting 64 bytes of data. Okay. So we're going to say byte 64. Okay. Now, remember in our actual data block that we're pointing to, the 0 byte contains, so the first 2 bytes actually contain that number of bins. So the first real bin value is pointing to 2.0 instead of that. So if you wanted to send from that data, you would want to create a pointer like this. Like if you wanted to send this across Profibus, you wanted to send one of these segments of data across, there you would go. You could use DP send across with that. And so it would move across with that. And that's where this byte 4 is this DB number here. Okay. We're going to talk about this weirdness, but for right now, we're only going to talk about this byte address of tag here, which represents that. That is going to be this here. Okay. If you notice, you already noticed something, we're going to talk about this goofiness right here. So we'll talk about that. But so that's the pieces of this tag. This byte 64. Oh, I may have misspoke there. Let me see something. Yeah, so no, that's right. That's right. I wanted to check and make sure, because this byte 64 represents the number of elements in the data set. So that's like in our transferring between like DP read and DP write dat, that is looking for a pointer, and it's telling you how many bytes it is. So it's getting that pointer. Now, Q and UN, you could just pass, you could create this data type and it would serve that information as well. But here's this byte 64, and that's actually contained in this right here, this second byte. Okay. Okay. So DB number in this instance is bytes 4 and 5. The address is kind of byte 8 and 9, and this how many bytes it is byte 2 and 3. Okay, the rest of it is pretty much going to be fixed for this. Like we're not going to worry about it. We're going to take one step at a time, because this is definitely going to be a little bit confusing to get through this. So we're going into our second full hour, and we're just getting to getting to this. So we're going into our third hour actually, and we're getting into this this concept here. So how do we use this? First of all, when we bring in our okay, I guess I can leave this here. Let me swap this over. Bottom right. So we're going to have to do some things, because when we bring in the any type here, it doesn't actually have all of the information readily available. And we're going to do what's called overlaying tags in order to kind of be able to individually tweak all of these variables. Because when we bring that variable in, I'm going to show you what it looks like when it comes in. Maybe it'll make a little bit more sense. So I have a simulation, a PLC sim running, so I can actually go online with this processor and observe this code. And if you're not familiar with how to do this, if you have PLC Sim Basic comes with TIA Portal, you just have to install it as a separate install. Like the license for it comes with your license for Portal, and you just click this on this and say start simulation. It kind of sets up everything. I've already done that because starting all of that does not go well on stream. But so let's look at what our we do this value here. We're just loading our temporary pointer, which is up here. We're loading our temp pointer, which is of type any, with the bin value that's coming in. So what it displays is that kind of like it displays this value here. I don't have my pen, so that's the value that we kind of talked about before about that P hashtag DB1 DBX0.0 byte length. So that temp pointer contains the entire data block. And so what we're wanting to do is modify these pointers and kind of tweak them into moving through what we want. okay? And because we want to load in one little section we want to load in one hunk of 64 bytes, we're going to load that in, do some stuff to it, and then load it back. So we're going to bring it into our block, change it up, do some calculations, and then load it back. And that's why A, it's an in and out, and then B, that's because we don't actually know how big that thing is going to be. That's why we're using this. So when it comes in, it has this DB1, which we know because we can see that over here. Oh, I haven't downloaded any of all that other stuff that I did earlier. But so DB1 right here, that's our bin data, our batch bin data block that holds all this stuff. That's DB1. The first place that it starts is at DBX 0.0 at the very beginning. These are all 0 based. And then the total number of bytes is 9602. And we can verify that by going down here and going all the way down to our last offset. And this is a time is 4 bytes. And so 9602 is the number of bytes that is in this data block. Okay, makes sense? Hopefully so. So let's go back to this guy. So that's what the pointer is. Now we want to take that because that pointer, we passed it in and it's pointing to the data block that we want to get the data from. And so the first thing we want to do is see how many bins are in this data block, because we don't want to overrun this data. We want to make sure to stay inside this data block, because using an any pointer and you start messing around with this stuff, you can easily move into someone else, like another data block's memory. And you can do, like, say for example, this has 9602 offset. That's how big data block 1 is. I can make a tag called DB1 and then name the area and do an offset of 10,000, and it goes into some completely different memory location. It is no longer in DB1. And so, because when you say DB2 comes in, it may not even be DB2. It might be something completely different. But say DB1's this big, and I have referenced something that's this big down here. Well, this much of it is going to be in the next memory location. You can see how that would be trouble. But so I want to check and make sure the size of this DB. There's a couple of ways to do it. I'm doing it just by checking this number of bins, and I know that each bin is 64 bytes. And so I can calculate in, hey, if I get over the number of bins, I don't need to look at anything else, and I don't need to copy back in. That's what we're doing there. Anyway, in order to get that one little piece of information, I need to take and look at the DB number and only look at the first 2 bytes and call it an integer. Okay, so my number of bins is an integer, and I'm going to use a function called peak, and there is a specific version of it called peak word. And the way that you can kind of call this is you can either go over here, and this is in a move operation, and I want to say it's in read write memory. Yes. And so if I wanted to use this function, I can just drag it over, and it kind of gives me this peak. And once you use it, you know, you can modify it by saying like peak word, and it'll also work. This isn't going to work because I don't have actual inputs in it, but that's how you bring it in. I would recommend doing that unless you just use this all the time and like is drag it in from your let me do that out. Yeah, So I was just hitting Control Z so I could actually just undo everything so I could get it back to where it's monitoring. But I would definitely use the instruction box. Okay. Right now I'm gonna so I'm using this peak word, and here is where I'm needing this peak word needs the DB number. It's not a pointer. It doesn't accept a pointer. It is looking for, as it shows here, peak word. It's looking for a byte, then a double integer, and then the return value for this particular version is a word. Meaning, if you're not familiar with that, you need to kind of understand what these things are. And this is kind of like more of a higher level programming topic of return values and all this stuff. But just know that these parameters that are going into this function, in this case, are the area, which is defined in this. Let's look at the this peak memory here. The area is defined if you're pointing to either input, output, bit memory, or a DB, or I guess you could do peripheral on 1500s. But inputs, outputs, bit memory, or your DB, you need to set that value. And so since we're working with DBs, that's always going to be hex 84. By the way, earlier in all of my little memory notes, I was writing hex values as 0x. In Siemens PLC, 0x is like represents hex in almost everything else, but Siemens PLCs, it's 16 hashtag, so 16 pound. That represents a base 16 number. Anyway, so the inputs to this are what type of memory are we accessing? What is the DB number? If you are accessing a DB, otherwise 0. And then what address are you wanting to be read, or what address are you actually wanting to read? So, and the way that you could think about that is a byte offset. Okay, because it goes from 0. Where do you actually want to read from? Okay, and so you're getting one word. This peak value, peak, P-E-E-K, peak function only returns one word. That's not adequate for what we're doing later, but right now the reason we're using it is because we are wanting to pull the number of bins out of the first word of our data block. So we use peak, and we're going to need our data block number. And you can hard code this if you need it, but the whole point of what we're needing is for that data block to be variable. Who knows what the data block number is? Okay. And so we're using a pointer. Problem is that this temp pointer technically doesn't have the data block number in an easily accessible format, but we talked about in the other thing that it, in the help file that we went through, it actually shows, it does have the data block number in it. Let's look at the any value here. It does have the data block number in it, DB number. It's bytes 4 and 5. So how do we get access to it? Here is a way. I'm gonna diverge from the 300s and 400s. So you can't do this method in SIMATIC Manager. So version S7, version 5.6. You can only do this in Portal, but it's called overlaying tags. And I've talked about it before, and we've used it for a couple of different things. I've got a video out there about it that's specifically about overlaying tags, but we're going to go through it again really fast. And so what I have done I have overlaid in the temp memory place. I have created this temp pointer, any. So like temp pointer is the any. And then I have done the at temp pointer by going through and making def pointer. And the first thing you do in your data type is type in the word at, and then hit enter. And then it will move that at temp pointer over into this little section here. And then I have created a user-defined type called pointer type that breaks down every one of these little values. And I would love to say that I came up with this method, but there is there's a guy on the Siemens support website, and I'm gonna give him a shout out because it broke me free. His username is Smiffy, and like, I don't know him, but Smiffy, if you ever end up watching this video, thank you for this. And it is a very simple way of going through and like actually being able to do this overlaying and accessing these tags. And it is amazingly simple. Thank you, Smiffy. Thank you for community and your contributions on the forum. But yeah, so I've created this pointer type that we've done UDT types. We've talked about them ad nauseum here, but it has all of the things in that help file that is available there. And so all of this structure, you have 2 bytes, and then a word, and then a word, and then a byte, and then a byte, and then a word. And so that's what you see here. Byte, byte, in this case, integer, byte, byte, and then a word. So that's what those are. And you can now use def pointer dot S7 code, def pointer dot DB number, which we'll use here, because that actually contains the DB number that creates this pointer. And so that is what this def pointer dot DB number is. It's the overlay of my temporary tag. First thing I do when I come in here is, once I get to this line, I sit there and say temp pointer, and I run it in, and there we go. Temp pointer. I just make a temporary copy because I can only do that overlaying of an any in a temp memory area. And so I have to do that. I make a copy, I make this overlay, and I use this peak word. And instead of typing in a DB number, I make this variable def pointer.db number. And you can look at this now. It pulls out and a byte offset of 0 because it's the first word all the time. I've defined that the structure of that data block to the first word is always the number of bins. So I can fix that. It's always a data block. And then I use this pointer. So now if I later come back and tie in, watch, we'll do this. We'll tie in a different, we'll tie in this DB1000 here. And then we're going to download, please compile with all the other stuff. Now, I've done that, and I go back and monitor my batch here and look at this. If I can bring it up, how's it? I guess this is not. I've got this if here, and I bet you that this result. Oh, I know what's happening. I downloaded this change. This is what I get for changing stuff on the fly. Let's download this. So obviously that stuff wasn't updating. And again, this is on PLC Sim. All right, so we're going to go back here, go online. Now this should be updating, and look at what we have here. This pointer is DB100, and if we go in, if we actually look at this definition, this definition pointer.db number is 1000. So it actually extracted out the DB number. Now, that DB is not structured correctly, so we need to go back and swap that up, but it's just proving to you that our code can accept this DB being changed and still referencing, as long as it's structured the same. Now, I'm compiling this and doing this manually, but there is a way to do that to where that DB is actually being created dynamically. And yeah, that's the ultimate version of this, is to where we have some either HMI recipes configuration or like a SCADA platform that interfaces into this block and says, hey, it creates that block, and this block, wherever it is, wherever it ends up, this block still works correctly. So that's our goal. Let's get back to batch count. Let's see. Let's pull this up. And so now we should see our pointer re-updated to 1. Okay, so that's pretty simple. Now what we're wanting to do is we are wanting to pull the data from this target bin, and we're going to do some stuff, and we're going to try to batch out 100. Now the code for all of the actual logic for that is not in there, and that's probably the only reason I'm showing you guys this. I'm just showing you this sort of stuff. Let's go back to this. So what we're trying to do is we're trying to pull in the data from target bin number 1. Okay. And so we have now, we're going to say, okay, our current bin number, we have to create an offset, because what we have is this data block that has all of these copies of this bin data. And so we're wanting to pull up this first bin number. So we've got bin number 1, bin number 2, bin number 3, bin number 4, bin number 5, bin number 6, all the way down there. We're wanting to pull all of this bin number data 1. We're wanting to copy it over and then do some stuff and then push it back. So that's what we're trying to do. So that's where we get our current bin number that we're working with. We're just going to say target bin number 1. So we can see this current bin number, target bin number is 1 over here. We want to take and create this byte offset, the byte address for our pointer, and then we want to pull that data. Well, right now the pointer is pointing to 0.0. That's not what we want. We know that our first bin data starts at 2.0. So we have to create this, and we want to create it dynamically depending on how many numbers of stuff. So we've already checked to make sure that our target bin number is less than or equal to the number of bins so that we don't overshoot our data. And so our current bin number, which we've shifted in, we're going to do -1, because we're always going to have an offset of 2 bytes. And then our target bin number, first bin number, is going to be at byte 2. So we want to do 1 minus 0 times 6, or sorry, 1 minus 1 is 0 times 64 plus 2. That's going to be our offset, because we want a 2 for our first one. And so 64 here is because our total number of bytes for each data set is 64 bytes. And so that's what this is. So target -1 times 64 plus however many offsets it takes to get there. And that is the offset number. Now, unfortunately, it's not as simple as this. If you're paying attention, you might have noticed this. There's another function here, this SHL. This is a bit shift left. And if you are not familiar with how bits and bytes work, this is not going to make sense to you. But from a logical standpoint, I'm going to show you here. And when I say logic, I mean like digital logic. Show this byte 8 and 9. If you notice, it is broken up into the byte address of the tag and then the bit address of the tag, which means normally, you know how we go D X 2.0. Again, I'm doing that with my mouse and I don't have my tab on the screen, but this is this. This is this. So there can be a total number of 8 bits. So you can go all the way up to 2.7 for the bit place of it. And then for this, for our example, for a very large data block, you're kind of losing a little bit. But notice you do have these additional 3. But we're just going to assume that this number of bits is enough to hold our offset. Okay? That's really bad. But so here's what we're going to do. These last little like the bit address is always going to be 0 in our case. So what this shift left takes all 16 of these bits. We're going to take our byte offset and just say, okay, we assume that it's small enough to fit into these 13 bits. And if, again, digital logic, you need to have a little bit of understanding on the digital logic of what numbers can fit into 13 bits. But assume that our offset length, say it's 100. 100 can absolutely fit into 13 bits. And we're going to take 100 and then we're going to shift all the bits over by 3 and call it a day. Okay? And that's what this bit shift left is. And like, honestly, if you aren't doing bit level access, this will work every time. Just use, so if you're always shifting by like byte, then this works. If you're shifting by a bit, then you have to add in those bits and it gets a little bit more complicated. So this shift left, just you shift it left by 3 bits and it creates this number that works in this any data type. And so like the byte address, the least significant byte, that's actually a word. And so it comes out and it shifts it by 3 bits over and you're good to go. And it actually shows this here because our shift should be 2, right? So it's 2, and then the bits are going to get shifted. So that 2 is going to be 0, 1, and then it's going to get shifted 1, 2, 3. So you're going to have the first 4 bits are going to be 0, and the first the 5th bit is going to be 1. And you can see, because this is in hex notation, you can see that there. So that first 0 represents the first 4, the second digit represents the second 4, and then so therefore. I might have to do a digital logic class later, but at this point, you're way in over your head if you don't know bit shifts and things. So that gives you that offset, okay? And now I know that we need a length of 64 bytes. So my data type that I made earlier is 64 bytes. And so we have an integer number, and then we have 64 bytes, 64 bytes, 64 bytes, 64 bytes, and just on and on and on and on and on. And so I bring in, the only 2 things I need to modify is the offset, because the DB number is going to be the same. So I need to change the offset of that pointer to point a little bit lower, in this case 2. And then I'm going to point to, and I want it to be that 64 instead of 99,000, whatever it was, the whole length. So I only want my section, because what I'm going to do now is I'm going to take that and I'm going to blind fill that into another set of data. And so yeah, so that's what we're doing here in these 2 lines. We are modifying the data in this here. So we're modifying the repetition factor, which overlaid, we call it the length, and then the byte offset. So that's what we're modifying. We're modifying those 2 things. And because of Smithy's method that he posted, it makes it really easy because we have that UDT type that we've overlaid onto it. All right. So now that we know how to actually modify those, we can tweak our pointer to, at first, it pointed to the full data set, the start of the full data set. So now we've shifted that down to address 2 and then shrunk it down to only the portion that we want. Now we want to move that over into and essentially move that into something that is 64 bytes big, which what we've done here, what I've done is I have created a local to this block. So a static address local to this block of an ag batch bin. Now these are the same ag batch bins that's over here. Okay, so that ag batch bin inside my function block is 64 bits or 64 bytes long. So 104 minus 42, I guess 108. No, 106 minus 42 is 64 because it's the same thing. So that is a memory space inside my local memory that is big enough to house the data from the tag that I want to like shove over in there. Now, the only problem in just saying, hey, move that over, is the function we're going to want to use is the function fill, F-I-L-L. And this function is available on 300, 400, and 1500. So in Portal and in SIMATIC Manager. So this fill function works. The only thing so far that doesn't work in the older version of the software is the whole overlaying tags. And there's other ways of doing that with creating overlays in interfaces. It's just not as simple. With that said, we're going to use this fill function. And what this fill function does is takes 2 pointers and says, hey, I want you to move this pointer, the information that's in that. So this block of data, fill this block of data with that block of data. And that's all it is. Just, it has no idea the structure. And so it is taking blank memory, like whatever, a block of memory, and moving it and filling up another block of memory. That's it. And the only checks it does is because you're using pointers, it checks to make sure that the space of the 2 is the same size. That's the only check. It doesn't know where this pointer is. It doesn't know where this pointer is. It doesn't care. It just does it. So only problem that we have is we don't have a pointer that is our destination pointer. So you have a source and a destination. And we only right now have our source because we've gone up here and up in lines 17 and 16, we modified the pointer, our input pointer. We tweaked it and modified it down. So we have our source but we don't have our destination. We want to put it into this data up here. And I'm being a little slow with this, but this is really hard concept to get. We're wanting to get this source data and shove it into this current bin data, which they are in different memory scopes. So you have global data and you have local data, and the pointers strip away all of the fact of like, hey, these aren't supposed to be communicating. We're not supposed to be able to shift this stuff back and forth. It strips all that away and says, hey, I'm going to move this and move it here. So that's what it's doing. So we have to have a pointer that points to this current bin, and it's actually pretty stinking easy. We create a data type of temp pointer. So temp destination pointer, call it an any, and it's a temp, so it goes away. Like after it goes into this function block, it goes away, it gets reallocated. So you get a pointer, and then you just say it equals pointed at the current bin, and wherever that memory location is, point it at it. And so here's the cool thing about it is you can look over here at, because I'm simulating this and I'm actually running this code, that current bin we know is in DB2 because this batch control instance that we have, so like ag batch control DB is DB2. And so it's pointing to DB2, DBX42.0, and it's 64 bytes. And all of that data comes from just this one little line. And if you look up and if you want to verify it, you can go up and your current bin data starts at 42, and we've already talked about it. It is 64. And we know this instance data block is DB2. So DB2, DBX42.0, byte 64. So it's doing what it is in one line. Super cool. And so now this fill function, it is just going to take the source, whatever is pointing, whatever that source pointer is pointing at, and move it over into the destination pointer. And it checks, like I said before, it checks if it's the right size, and that's it. Now, it does return an error code. I think it's a word, or maybe it's a dent. Let's see what it is. Come on, pop up. Return int. So I have temp int here, which if you don't, when you're writing a function block, go ahead and in every function block you make a temp int, a temp real, temp bool, make a couple of temp variables that you could just use, because here that temp int gets used a lot of different places, mainly as an error code return value. And if you're using SCL, you can actually see line by line what that temp value is. And so like here, the temp int is 0, meaning the error code 0. It executes properly. That data is getting moved around. Now, that's pretty cool. And because of that, we now are moving the first bin's data into our local current bin. And so we can shift this data outside here. We can shift it and move it in now. So let's do that, since just to kind of demonstrate what's going on here. So let's go into our batch control. Not that. So that's our instance data block, which, by the way, let's look at this. So this is our instance data block, batch control DB. And I've talked about that. If you don't know what an instance data block is, check out my OBFCFB video. Now, we're looking at this, and we can see that outside of the default value, there's like this bulk density that's been set to 10. Okay. We have a max speed is set to 0. So yeah. And we have a rated flow that's been changed to 1. Okay. So that's inside our batch, or inside the instance data block. So that is actually current bin. Okay. let's go to our bin data now, and we can monitor this and make sure that this isn't affecting my computer. So right now we can pull up bin 1 and we can see that the bulk density is 10 and the rated flow rate is 1 as well. So that checks out. Now let's just check to make sure that those aren't the same in everything, and we can see that that is not the case across the board. So let's take and look at one thing real quick. Let's go back to our OB, and remember we use that target bin in order to create and set our offset. So let's check and make sure that if we change our offset, that we change, and I could make that a tag, by the way, like an int tag, and then change it on the fly. Actually, let me just show you how to do that. That's fine to find that. And now we can actually go in and oh, one thing that I forgot to mention why you wouldn't want to use M memory is because it's much easier to set the default values. Like if M memory always starts at 0, there's no way to actually keep like a retentive value, meaning like if you set a set point of like in M memory, you're gonna have to set that set point every time that you go through. Like this in memory, if I reset this processor and like start it back up and stop it and start it, this will always be 0. And so we can modify control. Oh shoot. Yeah, I can't do it. Oh, yeah. Gotta do it in a, hate this. you gotta do it in a watch table. It won't let you do it right at that. Who knows why? What did I name that? Target bin? Wait a second. What did I do? What did I do? Oh, this is local temp. That's why. That's why I can't modify it. No. Delete this. Sorry about this. This is one of those like annoying things that I'm trying to prove a point, get distracted, and then we're gonna go here, take this, target bin, define the tag. We want this in not local temp, we want it in global memory, define that way, and now we can this away. There. Now that works. I bet you I can modify that now. Yeah, so temp memory goes away during every cycle. I still can't modify it. Yeah, there we go. So one, we go back to our code and monitor it. It should be the same as before. And yeah, so 10 seconds. We have this total runtime that we were talking before. There's our values. Our total runtime is 10 seconds. Now watch, this will change when I change this to a target bin 2, because it's looking at a value that doesn't hold those values. So target weight's still 100. My current bin, all this other stuff is 0, and so it jacks up. I end up dividing by 0. And so we have a problem there. And I'll show you that's because this batch bin, now it's not looking at 1, it's looking at 2, and it needs this rated flow. Say this is 2. Let's modify this to 2, and I will need a bulk density of 20. Now we can go back and look at this, and those values automatically show up here. So, and you look at our total runtime based on our calculation is 2.5 seconds now. Boom, which is what we're wanting to do. Like, and as you can see, I make notes to myself as I'm going through here that I need to redefine this, like calculating for ramps and everything, which I don't have that code in here. But I'm just proving that this tag sort of setup, while it's pretty stinking complicated, pointer type setup, you can make different things to where you don't really have to worry about what the data actually is. And you can take a data type of one data type, and you know that, say for example, you want to do some weird stuff and convert like a I don't know, make like a block that does like a what's called like a byte swapping. And so you would take the offsets and you would point to the first byte, and then you would move that to another pointer, and you could just swap the bytes, stuff like that. But for the most part, pointers are used for data that doesn't exist when you program that block. So you don't know for sure what DB number it is. You don't know how big the DB is, because you can go through, and now I sat there and did basically I made it to where the number of bins, I have a number of bin integer. Well, I don't technically have to have that, because I could go through, and because I know how big my bin data is, I can just divide this 9602 by 64, and I know how many bins I have. So there's another optimization, and then that way my programmer doesn't even have to set that like the configurator, whoever's doing that, doesn't even have to set that value at all. So yeah, I mean, I know this has been a very complicated topic, and honestly, it's just the start of it. And the last thing that I'll bring up is that the any pointer, bring up the help file on it. This any pointer is available, as you can see up here, for 300s, 400s, and 1500s only. It's not available on the 1200. Now, this concept of pointers and pointing to data and not actually containing the data is available on a 1200, but it's using a portal specific block or data type called a variant. And variants are a little bit stripped down, and I'll be honest with you, I haven't ever used them, and I didn't go through and learn variants for this because I had already used kind of the concept on 300s and 400s, and it has some code. And my dad's document that he wrote is based on 300s and 400s, and so it's all based. It's like really about any's, and so I wanted to be able to go back and run on a 300 as well, because we do have some of this stuff out there that's on 300s. So I mean, really, that's it. I mean, we kind of talked a little bit about structured text. I didn't go through it very much, but the big thing about structured text is if you have some like calculations, instead of using a calculate block, just make a structured text network and then use this sort of stuff. Just be careful though. Like, you can absolutely do whiles, and you can do a while loop that locks your code out like in a function block. So just be a little bit careful and conscious of ST. So and the final instance of this will have a while loop in it, to where it's grabbing multiple bins and like averaging data and like all sorts of stuff. So just be careful with that on your ST. But yeah, so it has been an interesting week, and we are like at almost 3 hours on this live stream. They keep getting longer and longer. But I'll try to condense everything down into 2 hours for next week. But we were off a week, so I had to expand it out a little bit. But yeah, if you've made it this far, be sure to just like hit that like button on it. So glad that you have made it, or I guess so glad that you have watched this video and like taken part in this community. And as it's growing, I really appreciate what everybody that's taking part in this, and the comments, the kind words, all of that stuff is wonderful, and I really do appreciate it. And as evidenced by this week, I'm still learning along with you guys. These pointers, concepts, and indirect addressing, that's something that I've only kind of like slightly done before with arrays. And so this has been a great week of learning for me, and I hope that you will learn in some capacity on this. And go back and watch different pieces. I'll go through and try and like do the chapters and chapter it out about the specific things to make it a little bit easier for you. But if you have questions, drop comments about specific things, and we may talk about this again more in depth, because this is a topic that requires a lot of depth. And maybe I'll do a section about kind of the digital logic and like binary, a little bit more elementary. We went through a wide gambit of stuff today, but I really do appreciate it. If you haven't subscribed, please subscribe, hit the notification bell so that you know the next time I go live and you can join in live. But until then, I appreciate you. Keep learning, and I hope you have a good weekend, and yeah, just enjoy your time. See you next time.